This is example 15. So this example focus more on nucleate boiling of water in a pan. So this is the question. What water is to be boiled at atmospheric pressure in a mechanically polished stainless steel pan placed on the top of a heating unit, as shown in the figure, that figure below. The inner surface temperature of the bottom of the pan is maintained at 108 degrees Celsius. If the diameter of the bottom of the pan is 30 centimeter, determine A, rate of heat transfer to the water, and B, the rate of evaporation of water. So what we have to do is we have to determine whether what is the rate of heat transfer, and then second one is the rate of evaporation. So this is the figure. So we have this surface at the bottom of the pan is 108 degrees Celsius, and then since the water is to be boiled at atmospheric pressure, so atmospheric pressure is 1 atm. As we can see in the appendix for the table E9 and refer to the atmospheric pressure 1 atm, we will see that the temperature T saturation at this pressure is 100 degrees Celsius. So that's why the water temperature is 100 degrees Celsius. So the pan is built up by a mechanically polished stainless steel pan. Okay, so next what we have to do is to determine the properties of the liquid and vapor. Okay, but before that we have to determine what is the region. Okay, we know that we have to determine what is the delta T excess. So the delta T excess is T surface minus T saturation. So we know that the T saturation is at 100 degrees Celsius because the water is boiled at 1 atm, which is the P saturation is 1 atm, and then the T saturation will be 100 degrees Celsius. So for the T surface is 108 and minus with 100. So from here we get that the delta T excess is about 8 degrees Celsius. This is in the range of 5 degrees Celsius. So this is delta T excess and 30 degrees Celsius, which this delta T excess falls under nucleate boiling. That's why this example is for nucleate boiling. So after we know that this question falls under nucleate boiling, therefore we have to refer directly to the equations of nucleate boiling. So we have nucleate boiling equation, peak heat flux, maximum heat flux, and then we have minimum heat flux, and the last one is film boiling. So now we already determined the delta T excess, which 8 degrees Celsius and falls under nucleate boiling. Therefore we directly use this equation. And then what you have to do after that, you have to determine all the properties here. So we have mu L, HFG, rho liquid, rho vapor, and then surface tension, CPL, TS, T saturation, CSF, HFG, and Prandtl number to the power of N. So CPL is a specific heat of the liquid. So from this equation, we will extract the properties from the table E9. So how can we at what temperature that we will refer to the E9 table? So we will refer all the properties at 100 degrees Celsius, which at T saturation. Okay. So now we take a look at here. We have a surface tension. The value is 0.0589 Newton per meter. So where do we get this value? Since we deal with water, therefore we directly refer to the table 10.1, and the T that will be referred in this table is at T saturation. So we have T saturation at 100 degrees Celsius. So at 100 degrees Celsius, we directly take out this value for the surface tension. Okay, so that's why the surface tension value is 0.0589 Newton per meter. So for the rest of the properties will be referred to the table E9 at 100 degrees Celsius. For example, we have here in the nucleate equation, heat flux equation, we have rho liquid, rho vapor, CPL, and then we have HFG and Prandtl number. All of these properties will be referred at 100 degrees Celsius. Okay, so this is the properties of water at 100 degrees Celsius. Now what we have to refer, what we have here, we have CSF and the n to the power of n, the Prandtl number to the power of n. So we have to determine what is the value of CSF and n. So to get the value of CSF and n, we will refer to the table 10.3. Okay, but now in table 10.3, we have to determine fluid heating surface combination. Let's take a look at the problem. Okay, in this problem, we will use water as a fluid, and then the steel pan is mechanically polished stainless steel pan. So for the mechanically polished stainless steel pan, so here we have water, stainless steel. All of these are stainless steel, and then we take a look at this description. Okay, mechanically polished, ground and polished, in the bracket, ground and polished, Teflon pitted, chemically etched. So now we have water, stainless steel, mechanically polished. Okay, we have fluid, water, and then we have stainless steel for the pot, okay, for the pan, and then that stainless steel is mechanically polished. So directly take out this value, CSF value, and then n is 1. So this is the value, CSF is 0.013 and then n is 1. Okay, so now we already know that the value of this equation, we will determine the heat flux at nucleate boiling. So therefore we take out this equation and substitute all the values. Okay, substitute these properties into this equation. Okay, so what you will get is, okay, from the Nucleate, I will not write down all the equation. I will give the answer. So for the Nucleate, after you substitute into the equation, you will get 7.21 times 10 to the power of 4. Okay, watt per meter squared. So this is the value for the heat flux. Now what we have to do is to determine what is the rate of heat transfer. To determine the Q value, Q dot, rate of heat transfer, what we have to do, we know that the Q nucleate, okay, Q is Q dot over area, because watt per meter square. So Q is watt, Q dot is watt, and then A is meter square. So this will gives you watt per meter square. So in order for you to determine what is the rate of heat transfer here, so you have to rearrange this equation. So Q dot equal to Q dot times with area. Heat flux times with area. So now we have to determine what is the area. So the area here, we will use pi d squared over 4 since the pan is in a circle. Okay, here if we see side view, so we will see the area is rectangular, but actually the heat transfer is on the bottom of the pan. So the bottom of the pan is in circular. So we will use circular area in order to determine what is the area here, because the surface, because previously we always use surface area. So now surface area, which is 2 pi RL. Now what we have here, surface area change into pi dl, since the area that will heat transfer occurs is here. So this circle area. So that's why we will use area is pi d squared. Okay, pi d squared over 4. Substitute the area. So pi diameter is 0.3 square over 4. You will get your area is about 0.07069 meter square. So after you get this value, substitute the Q and times with this unit, okay, this value, okay. So to determine the rate of heat transfer, so we have heat flux times with area. So our heat flux is 7.21 times 10 to the power of 4 times with the area is 0.07069. So now what we get here is your Q boiling will be 5097 watt. Okay, this is Q boiling. Okay, Q dot boiling. So you already get the answer for the rate of heat transfer for the boiling. And then what we have to do, there is another question asked us about the rate of evaporation. So for the rate of evaporation, we will use this equation where we have Q dot equal to M dot HFG. Okay, so we want to find what is the rate of evaporation, which means we have to determine what is the mass flow rate per second, mass flow rate of vapor. So rearrange this equation, we get what is M dot. M dot is Q dot over HFG. So your Q dot is this value. So 5097. You divide with HFG, the properties that you refer to previously at 100 degrees Celsius, and you get to 257 times 10 to the power of 3. Please make sure that the value is the same to cancel out the unit. Okay, if it is not the same, you have to change it before. So you will get 2.26 times 10 to the power of minus 3 kilogram per second. So this is the rate of evaporation. Okay, you already answered the question. And again, what you have to do first, you have to determine what is the delta T excess. This is the method or the steps that you have to follow before you determine which region and determine which equation that's suitable to answer for that problems. Especially this is specifically for boiling. So what you have to do first is you have to determine what is delta T excess for that question. Okay, determine the delta T excess. Then after that, you have the range of the nucleate boiling, film boiling, transition boiling. You have to remember that range. Okay, after you determine the delta T excess, you have to compare with the region. If the region falls, for example, like this equation, you have 8 degrees Celsius and falls under nucleate boiling, which the region of nucleate boiling is in between 3 degrees Celsius and 5 degrees Celsius and 30 degrees Celsius. That is the range of nucleate boiling. You have 8 degrees Celsius and falls under this range, and then directly refer to that equation. Okay, nucleate boiling equation, you determine that is the nucleate boiling, and then you refer directly nucleate boiling equation to find what is the heat flux. And then after you determine what is the heat flux, if the question asks you about the heat flux, that is the end for your calculation. If the question asks you about the rate of heat transfer, then you have to use this equation. Okay, change it into Q dot boiling. And in this question, surface tension, you will refer at T saturation. Okay, take a look at T saturation. Not all saturation temperature will be at 100 degrees Celsius. You already learned about this saturation temperature in thermodynamics. So I think you already know about the T saturation. So for the water at 1 atm, the T saturation will be 100 degrees Celsius. That's why this question refers to 100 degrees Celsius, okay? Because the T saturation is at 100 degrees Celsius for the surface tension. And then to refer for your CSF and N, you have to refer to the table 10.3. So check your question, what is the combination, okay, for the fluid heating surface. Okay, take a look carefully at this table. What for this question, water and stainless steel, and then mechanically polished. You have to refer CSF at mechanically polished and take out the value for N and CSF. Okay, careful at that point. Okay, that's all for this example. Thank you.